Hi all, this is Mr. Yeager for chemistry. A couple more gas laws that we're doing this year. So we've already gone over Boyle's, Charles, and Gay-Lussac's, and also the ideal gas law. The last three I want to talk about is the combined gas law, and then two more. We have what's called Dalton's law of partial pressures and Avogadro's law. After doing the other ones, these won't seem like anything that special, okay? But you can see how, again, everything comes together. So the combined gas law is exactly as it sounds. It is combining Boyle's, Charles, and Gay-Lussac's law all together, and our formula is PV over T equals PV over T. All right, so that one's pretty straightforward. All right, Dalton's law of partial pressures. Dalton's law of partial pressures basically looks at the fact that each gas independently creates its own pressure. So if there are multiple gases in there, each will have its own, and then we just simply add them all up, is what we basically do. All right? So that's really it. The total pressure will equal the pressure of gas 1 plus pressure of gas 2. You will see in some of the problems that you work through, it'll often say that the gas is collected through water displacement, essentially seeing how much the water does change based on the amount of pressure that's on it. And so therefore you might run into this where you're going to see it say the barometric pressure, where barometric pressure is basically the atmospheric pressure, the total pressure. Okay, that's what that means, is just total pressure. All right, so barometric pressure equals total pressure. And all you got to do here is it's going to be the pressure of the gas plus the pressure of the water. Okay, the vapor pressure that's always over that water at a particular temperature. Okay. So that's it for that one. It's just a kind of an addition-subtraction problem. And then the last one we got is Avogadro's law, which basically relates volume to moles. Okay, you can see that's V1 over N1, V2 over N2. So there's a direct relationship. As you increase the number of moles, they're going to take up more space. How about that? All right, so let's just try a few problems so you can see how this goes. All right, so you have a 2-liter container of helium gas. Is at a pressure of 1.5 atm at 25 degrees. What is the new pressure of the gas? Is moved to a 1-liter container at 50 degrees Celsius. Right, that's good English. All right, but you can see here, this is going to be a combined gas law problem. I mean, that might be the toughest part of this unit, as we've talked about, is just going, which law am I doing? My suggestion is, again, recording down what you have of everything. So we basically have an initial volume, 2.0 liters. We have an initial pressure, P1 is 1.5 atm, and we have an initial temperature, but remember we need to change temperature to Kelvin, so 273 plus 25 equals 298 Kelvin. On the other side, we have, let's see here, we're solving for pressure, so we don't know what pressure 2 is. We got volume 1, or volume 2 is 1 liter. And then our new temperature is going to be 273 plus 50. So that would be 323. So based on the fact that I have all volume, pressure, and temperature, and I have multiple things changing, this must be a combined gas law problem. So I would set it up as PV over T equals PV over T. And so I would have 1.5 times 2 over 298 equals P times 1 over 323. And you can again do either cross multiplication, however you want to kind of do your algebra with it, where you can kind of figure it all out. If it's done right, let's see here, 323 times 1.5 times 2, I'm basically cross multiplying, divided by 298 times 1, and I'm getting a pressure of 3.2 atm. Maybe 3.3 if I round it right. 3.3 atm. All right, so that is our new pressure. All right, which makes sense because I'm decreasing the volume. Volume and pressure are inversely related, and I'm increasing the temperature. Pressure and temperature are directly related. I should see this increase. This is a little bit tougher sometimes to predict because you might have opposite reactions to what you are changing. So again, we just basically solve. Our second one, Our second one we got here. I have a 5 mole sample of neon, takes up 5 liters of space. How many moles would be present in a 2-liter sample or space? Okay, well, you can see here, I have moles and I have liters. This must be Avogadro's. Okay, and Avogadro's law is V1 over N1 equals V2 over N2. So if I solve this, this would be V1 is 5 liters divided by 5 moles. This is going to be pretty easy, but there you go, equals 2 liters over X moles. Well, you can cross multiply or just realize this is a 1-to-1 ratio, but 10 divided by 5, guess what, is 2 moles. But that's it for that one, okay? If I decrease the volume, I'm going to have to decrease the amount of moles present. So that's Avogadro's. The last one to show is Dalton's. And so for this one, we know it's Dalton's because you see basically you have a container with multiple gases present. In almost every other problem, there's only one gas present. In the container, there's 250 torr of neon, 600 torr of argon, 1,000 torr of xenon. What is the total pressure in the container? This is Dalton's. All we do is add it all up. So it would just be 250 plus 600 plus 1,000, and that should be 1,850 torr. Okay? So those you just got to read carefully. I mean, if I give you the total pressure, and maybe I'm saying what's the pressure of the xenon, we would subtract all those partial pressures from the total and find the partial pressure of the one individual substance. And that's basically it. Like I said, pretty quick. Thank you.